Last time we introduced functions and discussed how to represent bounded functions using discrete numbers. Computational imaging consists of estimating object functions from measurement functions. The relationship between the measurements and the object is called a transformation. Transformations often correspond to physical processes, as illustrated here by diffraction and focal imaging. On the left, we have a incident wave coming here, and then it hits a diffracting slit and then diffracts into a diffracted wave here. So the transformation we'd be interested in describing would be the wave distribution on the incident plane and the wave distribution diffracted. Those are two different functions that we would describe as some kind of transformation. On the right, we have a three-dimensional object described by distribution f of x, y, and z, and it transforms into a two-dimensional image g of x prime, y prime on the focal plane of a lens. This is a relationship between these. The relationship between these two distributions is a transformation that we'll model as we get into this text. In these two cases, the object and measurements correspond to different distributions in different physical spaces. The optical field induces the object induces an optical field in one space, and then that propagates into the measurement space. Today, we'll discuss abstract features of common transformations and how we model them in imaging system, including both physical transformations and mathematical transformations. Let's get started. Computational imaging. Episode 3, Transformations. So we're in Chapter 2 of Computational Optical Imaging, considering forward models, and we're in the third section talking about transformations of functions. Here's an example of a transformation. This is a radon transform. We have the original function, the original object distributions on the left, and then corresponding to each object distribution, we have a radon transformation on the right. The radon transformation has on the horizontal axis angle theta, and on the vertical axis displacement L from the center. So basically we're measuring a ray integrated through each object. So if we, for example, follow the ray that I just drew, we would integrate the bright spots where it intersects. And so you see this kind of sinogram, as it's called, the transformation of the object to its measurements when we measure ray projections through this. This will be the subject of Chapter 2 when we talk of projection tomography and ray imaging. You see the different transformations of the different objects. Here's another transformation, the Fresnel transformation. This occurs when a wave diffracts. So this is an image from Chapter 4 of the text showing diffraction of a field from various distances at different wavelengths. And you see there's some harmonic modulation on the fields, so they separate into separate spots as they diffract under the Fresnel transformation. And each one of these images corresponds to a distribution in a different plane. So this would be the input plane, and the 5,000 wavelengths, 25,000 wavelengths, 75,000 wavelengths, where we've diffracted different planes. We have different distributions, and a transformation describes the relationship between these different fields. This is a cross-section of a Fresnel transformation. This is another plot from Chapter 5 of the text showing defocus of waves. Here at the upper left, we have a in-focus impulse response for a coherent imaging system. Each one of the plots has three curves plotted. One is the amplitude of the field distribution in each plane, and then the solid curves and the dotted curves correspond to the real and imaginary parts. So we'll have complex valued functions and study their transformations as they diffract under the Fresnel transformation. So these are going to be important transformations for us to understand in modeling imaging systems. So those are two examples where the transformations occur through a physical process. We're also going to find great usefulness in the use of mathematical transformations of image data that we've already captured. So let's look at an example. Well, I can't whistle and talk at the same time, so let's get back to our analysis. Here's a plot of the sound wave from that video clip, and at the upper left, and then at the lower right we have its Fourier transform. Let's talk about how we turned that sound wave into a computer plot and how we calculated its Fourier transform. Here you see the sound wave consists of these four dense blocks of signal going up over time, and it goes from 0 to 6 seconds. And somehow the Fourier transform has frequencies going up to 10,000 hertz, and we see peaks at some specific values of frequency. So before we get into exactly what that is, let's play the sound again just to remind you that we have these four peaks. The video clip was recorded with the webcam, and then that clip was loaded into Adobe Premiere, where the audio was pulled out and saved as an MP3 file. You could use a lot of different programs to grab the MP3, but then once we had the MP3, it's loaded into a NumPy array using the Jupyter Notebook that's on the Arizona Camera Lab Computational Imaging GitHub site, which is shown on this slide, but which is, of course, used throughout the course. Now we can't really see much on the plot of the sound wave at the upper left because the MP3 format stores 22,000 samples per second, even though there aren't actually 22,000 samples stored in the recording. But so we have these 130,000 data values, and when we look at the trace, we don't really see those resolved. We do see peaks in the Fourier transform, though, so let's try to understand where those come from. We can see those by zooming in a little bit into the audio file, which we do on this next slide, where we've zoomed into just a 50 millisecond time sample at the upper left, and then we've zoomed in on the Fourier transform. We can see a first peak on the Fourier transform at around 500 hertz. If we look at the plot on of the time samples, you can go and count over here. So if we go from like 0.92 seconds, you would go 1, 2, 3, 4, 5 waves would get you to 0.93 seconds. So over 1/100th of a second, we see about 5 waves, which correspond to that first harmonic we see at 500 hertz. So these harmonics come from resonances of my hands. That basically the modes that we talked about in the last lecture are things that exist within the cavity of my hands, and when I blow on it, you see frequencies that arise from that. So this is an example of a transformation. This is a Fourier transform from this linear temporal signal to its Fourier transform, which we use to understand properties of the object. We can visualize this data in other ways. Here is a short time Fourier transform, also implemented in the same GitHub notebook. Now what this is doing is taking the Fourier transform of a sliding window of a finite length over the signal. In this case, I think the window is about 50 milliseconds. And so we see the four regions. As you look in time horizontally, you see the four regions where the whistles occurred, and you see various frequencies occurring for various amounts of time. So transformations that we'll be interested in the course don't have to conserve dimension. Very commonly, we will, as we saw with the imaging situation, go from a three-dimensional object to a two-dimensional measurement. So that's a transformation from a three-dimensional distribution to a two-dimensional distribution. Here we're visualizing a one-dimensional signal as a two-dimensional spectrograph, and we'll also find examples where that's a powerful thing. So transformations are just a central piece of what it is to analyze imaging systems. So transformations can be of various forms. So anything that transforms an input distribution into an output distribution we would call a transformation. We call a transformation linear if it satisfies the following property, that the transformation is linear under addition and scalar multiplication. So if we have, for example, two input distributions, F1 and F2, their sum as multiplied by some scalars is the sum of their transformations multiplied by the same scalars. So alpha F1 plus beta F2 transformed gives us alpha times the transformed version of F1 plus beta times the transformed version of F2. Any linear transformation can be described by a integral form. So we could describe the transformation to the transformed distribution g of x from the input distribution f of x prime using a kernel h of x prime and integrating over that kernel. We know this is true because of this linearity property of a linear transformation. One distribution we could put in would be the Dirac delta function. If we input the delta function, we would get the impulse response h of x prime, and then any function can be represented as its integral over the delta function. So because of the linearity property of a linear transformation, we know that any linear transformation can be implemented in integral form. So the Fourier transform is an example of a linear transformation. We have a function f of x, and it's the impulse response in this case is the harmonic function. So any point f of x would produce a harmonic wave. And so our kernel h of x prime, which here we've written h of x and u, with u corresponding to frequency, is the harmonic function. The Fourier transform has an inverse transformation that would go from Fourier space back to normal space. So f of x is going to be basically the inverse Fourier transform of f of x of f hat of u, where all we've done is conjugate the impulse response to get the inverse transform impulse response. We'll be interested in a particular kind of linear transformation, shift invariant linear transformations, of which the Fourier transform is not a shift invariant linear transformation. Shift invariant linear transformations have the property that if we look at this kernel, the impulse response h of x prime, it has the particular form that it only depends on the distance between x and x prime. So the kernel becomes h of x minus x prime. And what this means is that the impulse response is independent of the input position. If we shift the input position, all that would happen is we'll shift the output position of the impulse response. This is typical of imaging systems where the h would be a blur function that occurs wherever there's data within the image. But the Fourier transform is not a shift invariant linear transform, but it is very useful for us in analyzing shift invariant linear transforms due to the Fourier convolution theorem. If we look at our shift invariant transform and take the Fourier transform of g of x, so we'll look at the Fourier transform of g of x, which is the Fourier transform of this convolution between the input f of x prime and the impulse response, we can find the following very interesting thing. So we've added a second integral here over x to take the Fourier transform of g of x and taken that into the integral, and then changed variables within the integral to separate the two integrals. And we see that the Fourier transform of g of x, this g hat of u, is the product of the Fourier transforms of the input distribution and the impulse response. So what the Fourier convolution theorem allows us to do is transform these integral forms of a transformation into algebraic multiplication between the Fourier transform of the impulse response and the Fourier transform of the input. These pairs, the impulse response and its Fourier transform, are called the impulse response and the transfer function. The Fourier transform of the impulse response is the transfer function of the system. And so basically any shift invariant linear transform is a filtering operation that basically the spectrum, the Fourier spectrum of the input distribution, is filtered by this transfer function to produce the spectrum of the output distribution. We can see this happening in imaging systems. Let's take an example of a particular kind of impulse response. So a common impulse response would be the Gaussian distribution. So this is a localized impulse response that as sigma gets smaller, they would be more and more localized. Its Fourier transform also turns out to be a Gaussian distribution. So the Gaussian has the property that its own Fourier transform is also a Gaussian. Here's plots of input distributions, or the impulse response for various values of sigma, the width. So as sigma gets larger, the impulse response widens. On the contrary, as sigma gets larger, the narrower the transfer function becomes. and so that the spectral transfer of the system gets narrower as we blur more. And so on the left we see the impulse response for various values of sigma and the corresponding Fourier transform or transfer functions on the right. So the effect of these impulse response is to blur the image. So if we have this kind of idea of a Gaussian impulse response for various weights, here we have a signal that was the same signal we looked at the Fourier transform of in our last discussion, and we've convolved it with the impulse response for various values of sigma. So at the upper left, sigma is 0.01, and the signal is relatively unperturbed. But as we increase the width of the impulse response, we see more and more blur as the system is transformed. Now, as with all of the plots that we show in the course, you can go to the course GitHub site and look at the code that did this. The interesting thing here, of course, is that we use the convolution theorem. So our signal is the same as it was in the last video. It's this f of x defined to be this kind of ramp, and we calculate its Fourier transform using NumPy's FFT function. Now, FFT here stands for fast Fourier transform. So once we have data in discrete form, it turns out that the Fourier transform can be broken into a multi-scale set of operations that, instead of requiring n-squared operations as you'd have for a normal vector matrix multiplication, can be implemented in n log n operations, which makes it much faster than, for example, directly calculating the convolution at every point using integration. So in this case, to convolve with the impulse response, what we do in this code is take the Fourier transform of the input signal, multiply the Fourier transform of the input signal with the Fourier transform of the impulse response, which is shown here, and then we take the inverse Fourier transform of that multiplication to calculate the blurred function. And so if you go look at the code, that's exactly what you'll see. So that's our introduction. Next time, we're going to move on to section 2.4 of the text, and we'll talk about sampling and discrete analysis, how we can use samples of a signal to represent the actual signal. Our analysis there is based on this very famous paper by Claude Shannon from 1948. Shannon's paper, as you see here, has 154,000 citations. I asked ChatGPT what was the most cited paper ever, and it told me work by Oliver Lowy on protein measurement from 1951 has been cited 235,000 times, so a few more times than Shannon, but not much. Albert Einstein's most cited paper has 25,000 citations. So clearly this work by Shannon is extremely important, and we'll discuss it in our next video.